Welcome to the first video of Talon Tech Teaches. Today's problem, projectile motion. Projectile motion is a big problem in FRC, but FTC as well, with games like Decode. With projectile motion, there's three main formulas that you have to know. Each of these equations solves for a different value: final velocity, x displacement, and final velocity squared. Each of these solutions, however, comes from a different number of variables and constants, which we'll go over. It may just look like a lot of crazy symbols, but we have initial velocity here, acceleration, and time. And when we do this equation, it gives you final velocity. To get x displacement, you start with your initial x value, your initial velocity, your time, your acceleration, and your time squared. For our final velocity squared, we have our initial velocity squared, our acceleration, and our x displacement. These are the basics of all kinematics equations, and we can use these to find the projectile motion of a 5-inch wiffle ball flying through the air, which we'll now do. I've illustrated here one of the problems that you may face when solving for your Decode robot. What we have here is our initial height of our launcher, the parabola of its motion, and then here we have our goal, which is going to be 1 meter. These values aren't precise, but this is just a leaping off point and just a proof of concept for solving projectile motion problems. So we're going to start by writing out what we know. What we know is going to be our angle, because that's already decided in your design. So let's say that's 45 degrees. What we also know is your initial velocity, because that's also decided by the TPS of your turret, your rotation per minute. We're going to put this at 15 meters per second, pretty accurate. And we also know our initial x, or y. So y0 would be 0.5 meters, and you know your ending y. y1, 1 meter. An important concept to note is that the path of this ball can also be constructed with x and y. So here, as you can see, follows the path. We have an x component, which is going to be our initial velocity in the x, and we have a y component, which is initial velocity in the y, as well as acceleration in the y. So here, what we're going to do, since we know this angle is 45 degrees, we're going to do a little bit of trigonometry to determine our x displacement, our x velocity, and our y velocity. And this is all to find our vx. Because by lowering our vx, we can create a more consistent shot. So that's what we'll be solving for. What I'm going to write out next to help us understand is some trigonometry. So this is basic, which should be learned in most geometry classes, but we're just going to write out sine theta equals opposite over hypotenuse, cosine theta equals adjacent over hypotenuse. Now, if you haven't grabbed a calculator already, you might want to, because it gets pretty rough without a calculator. So we know our instantaneous velocity at this angle is going to be 15 meters per second, because that's what we're launching at this 45-degree angle. So now what we can do to plug in, we're going to find our initial velocity in the y, sine 45 degrees, 45 from here, equals opposite over hypotenuse is 15. Now we multiply both sides by 15. Which equals your velocity in the y initially. If we grab our calculator, solve that out, make sure you're in degrees and not radians, we get an initial y velocity of 10.6, meters per second. Now the same can be done for the x. Cosine 45 degrees equals adjacent over hypotenuse. Multiply both sides by 15. 15 times cosine of 45 is also equal to 10.607. This makes sense because 45 degrees is the middle between 90 both ways. So it's taking half from the x and half from the y to get to its solution. If you want to use Pythagorean theorem, you can validate that this is 15 meters per second on the hypotenuse right here. So now that we have our x and y, what we can now find out is our ending x and y. Although in this season air resistance is not negligible because of the nature of the gopher balls, we're going to ignore it on the x and y as well. But we will be using acceleration on the y and no acceleration on the x, because what we're assuming is that there's no resistance to our motion on this kinematic plane. What we're looking for now is a hypotenuse of this little triangle right here, at this instantaneous point before it reaches the goal. So if we were to draw that out, oops, we know our x already because our x remains unchanged. So this will be 2.607 meters per second. We don't know our hypotenuse, our c, and we don't know our b either. So now what we have to solve for is Vy, and once we get that, we can solve for our c squared, this, using our a squared and b squared. We can imagine our y component going up and down while our x goes this way. By doing that, we can split our x into this, as we've done with 2.607, and our y by going straight up. So to find its point 0.5 meters above its initial starting point, we're going to be using this equation, final velocity. So what we're solving for is Vx squared. We have our initial velocity squared, which is 10.607, plus 2 times acceleration, which for this problem we'll be using 10, but that's used pretty interchangeably with 9.8. So we have negative 10 times x minus x0. Our x here is 1 meter, that's our goal, and our initial x0 is 0.5. So what we have here is 1 minus 0.5 times 0.5. Now, if you solve that out, you get Vx squared is equal to 102.508. Now we take the root of both sides, and you get Vx is equal to 10.125. So now we can plug that in to this side of the triangle right here, 10.125. And now using the Pythagorean theorem, we know a squared plus b squared equals c squared. We can take a squared, 10.607 squared plus 10.125 squared gives you a result. C squared is equal to 215.024. Now, of course, take the root of that side on both sides. We have our C is equal to 14.66 meters per second. Now, we know our ending velocity, 14.66 meters per second. But if you wanted to find a lower velocity, what you need to do is change your angle and change your initial velocity. Now, playing around with those constants and variables, that'll get you lower or higher velocities, which may help or hurt your case.